You have fallen into Event Horizon with John Michael Godier. Joining John today is Dr. Brian Keating. Dr. Keating is a physics professor at the University of California, San Diego, and the director of the Simmons Observatory, specializing in the study of gravitational waves created during the early stages of the Big Bang. Dr. Keating is also a pilot and is the recipient of the 2007 Early Career Award for scientists and engineers for his work with BICEP.
Quick note here before I start talking with Brian. It is summer, and for many of us in America, we are about to celebrate the 4th of July. And to let all of you in on a secret about the team that makes Event Horizon, we all really love a good video game. That's why I'm happy to let you know that today's video is sponsored by Fishing Clash. Fishing Clash has you traveling all around the world to fish in different locations with some of the most realistic graphics I've ever seen in a game I can play on my tablet or phone. Featuring brilliant locations such as fishing off the coast of Florida or a nice day on the Colorado River, with each location having a wide variety of fish to catch. Fishing Clash will keep you busy with PvP modes, competitions, and events. And speaking of events, starting from the 4th of July, you can jump in on a special in-game event dedicated to the U.S. Independence Day. You started as a new player in Florida fishing for all types of fish while enjoying the beautiful views and realistic graphics. And as a neat bonus, you can catch bottles with the Founding Fathers' signatures. And the developers tell me they've prepared something else that's truly special. To find out, use my gift code, Event Horizon, that's Event Horizon with no spaces in between, to get a special reward for new players for a total value of $20. With my gift code, you get a 3-star rod, 1 dolphinfish lure, and more. So join me on Fishing Clash this holiday weekend and support the channel by downloading the game and using our gift code, Event Horizon. Links are in the description below.
Remember to subscribe to Event Horizon so you never miss an episode.
Dr. Brian Keating, welcome back to the program.
It's such a pleasure to be with you, John.
How you been, Brian? You seem like you've been busy.
Well, I did publish my third book, an audio book, and to do so, I had to become a publishing company, which I never thought I would be. I never thought I'd write a book. I never thought I'd write a second book, which is quasi-self-published. And I certainly never thought I'd start a publishing company, all while teaching and raising a family, and running an experiment with my colleagues called the Simmons Observatory, and a YouTube channel and a podcast. I get really bored pretty easily, so I always have to keep busy.
How does one get Albert Einstein to write the foreword of a book these days?
Well, you have to reincarnate someone of his intellect. And you know, because you've had on Frank Wilczek, who is a Nobel Prize winner, who did his Nobel Prize winning work at the age approximately that Einstein did his work, in the age about 23, 24, and is only, like Einstein, continued to get more and more brilliant. So Frank agreed to read the foreword by Albert Einstein, which is a famous foreword in the history of scientific books, wherein Einstein basically says, this book, The Dialogue, which I published in audio form for the first time in history with Carlo Rovelli and my friend Lucio Piccirillo and Fabiola Giannotti and James Gates. We published this really to pay homage to the founder of the scientific method, Galileo. So I think getting people on this love, passion, whatever you want to call it, curiosity project, it didn't take much convincing. And Frank is such a wonderful guy. And it was natural to have him read the part of Einstein, although I kind of felt guilty that it also could have been Jim Gates, but Jim has such a wonderful voice that I wanted to save it for the longest of the forewords by the translator, Stillman Drake, who's a towering historian in the field of science.
Let's go into that. Galileo as the founder of the scientific method. Now, what differentiates him from his predecessors? What is the difference between Galileo Galilei and a predecessor, Giordano Bruno?
So what Galileo did so uniquely, and of course he didn't do it in every field of science, so to call it the scientific method, as I've pointed out in conversations that you and I have had in the past, there is no one scientific method. It's not like you go to the checklist and perform an algorithm. That's not typically the way science gets done, but the general framework that you either are guided by the need to explain existing evidence, or a prediction of unseen evidence so far and how to acquire it in a self-consistent, coherent way. These are facets that are attributable to Galileo. So the most famous one that I can think about was he felt that it was incorrect to believe, as Aristotle did for 2,000 years and before him, that a heavier object fell faster than a lighter object. So he did experiments. Of course, the apocryphal one of him at the Leaning Tower of Pisa may be just that, apocryphal, but it may not be. We actually don't know. But he certainly did experiments with inclined planes and different masses and so forth, where he showed that you could drop a light object and a heavy object and they'd arrive at the ground at the same time. But even before he did that, John, he actually conducted an experiment without any equipment whatsoever, which Einstein would later call a Gedanken or thought experiment. And that was to say the following. Imagine you have a massive piece of rope, and this is just massive rope. And it's super thick, like those guys at the gym use, and they just, bulk up their arms, right? Now, imagine dropping that from a high tower, and then in midair, you cut it in half, or you set off a charge and blow it up in half. Or not even in half, you blow it in a 1/4 on one side and 3/4 on the other side. According to Aristotle, that object should hit the ground at a different time than the lighter quarter of the rope. And of course, that's absurd, right? If you put a brick on top of a much, much more massive bowling ball, say, it's not like the bowling ball will out-accelerate the brick. And Aristotle could have done these experiments, but he didn't do it. Galileo did. And then he went further, and then he determined the theoretical underpinning of it. And this was all before, of course, his later coming scientist that he influenced, which was, of course, Isaac Newton. So Bruno and others had great theories. I mean, Bruno's claim to fame, and for which he was burned at the stake in 1600, was that every star was basically he called them another world. It's not clear if he meant that there are other planets or stars, but that's, of course, true. But he didn't do any experiment or do anything. There was no data collection. There was no iteration. There was certainly no consensus building, right? I mean, he got burned at the stake for a reason, whereas, Galileo built up a tremendous amount of goodwill up until the very end when he published the Dialogue, the book that we just self-published in audiobook format for the first time.
So this anti-experimentation stance of the ancient Greeks, essentially, Aristotle, why not go out and verify? Why do you think it didn't occur to them to do it? Did they have like a cultural systemic problem in their thought process that kept them from going out and dropping the feather?
That's a really good question, because in the context of human biology, of course, you're right. They did have a cultural overbearing kind of prime directive, which was you're not allowed to, do dissections and tamper with things that have a soul and so forth, right? So there was a predisposition to not experiment in the biological or medical sciences. And perhaps there was this kind of antipathy towards doing experiments whatsoever. And in fact, some of those kind of trends reversed themselves as early as the 1900s, when the first Nobel Prizes went exclusively to experimental discoveries and not to any theoretical discoveries. And for that reason, Einstein was prevented from winning a Nobel Prize. Theoretical discoveries, if you will, were considered beneath the great kind of Germanic and Aryan traditions that held sway for the first 20, 30 years of the Nobel Prize. So even though Einstein had this phenomenal track record dating back to 1905, he didn't win the Nobel Prize until 1921 because real Germans and Aryans did experimental science. So it was exactly the inverse of what prevailed during the previous 2,000 years almost. So it is a good question as to what was the barrier to doing such experiments. Certainly today we don't have those barriers, and we do apply the evidence gathering tools as Galileo did. And as I said, he didn't do everything. He didn't do dissections, and he didn't do chemical reactions and use the scientific method there. But what he did do is astronomical observations combined with theoretical conjectures that were then tested and iterated upon. And then, of course, he did it in the physical laws as well. So it's quite striking that one man did so much for so many with the power of his brain and the curiosity to actually go out and do experiments.
Do you think that as a result, and I ask this as a pure question, just completely off the floor, is science now more efficient than it once was?
It is and it isn't. There are prevailing trends in science that are very positive, that we go out and have to now pick high-hanging fruit because most of the low-hanging fruit has been picked by brilliant people that came before us. We have maintained some of the tradition of the Galileos and the Newtons and so forth to come up with new ways to test and build consensus. So it's no good to have a personal theory. And I see this a lot with aliens and so forth. And I see it on sides that I fundamentally agree with as well, right? Because people like Elon Musk or Michael Shermer, I've had one of the two of them on my podcast, will say things like, well, cell phone cameras have gotten so great, yet the evidence is so bad for UFOs. So I fundamentally agree with that. I am not in the camp that believes with a full faith and confidence that I'll bet my neighbor's dog's life on the existence of not just aliens existing, but them visiting us consistently for many decades, if not more. And yet I feel like the scientific consensus espoused by folks like Musk or Shermer or whoever is fundamentally not an honest application of the scientific method. It's not to say they're not right. In other words, Galileo was wrong and Einstein were wrong many, many times. And some of the things they were wrong about being wrong about. Like famously, Einstein's biggest blunder was the non-existence of the so-called vacuum or cosmological constant. Well, that blunder that he made was actually to say that it was a blunder because in 1997, folks like Adam Rees and Brian Schmidt, who have been on guests on my podcast, won the Nobel Prize for the discovery that the universe is pervaded by dark energy. So the thought that we look to these kind of gurus, whether it be a Musk or a Fauci or anybody, as if they're or an Einstein or a Galileo, as if they're infallible, I think that undermines the scientific method. And the famous quip by Galileo was that the Bible tells us how to get to heaven, not how the heavens go. So, and I agree with that, but he's also saying things like authority, the humble reasoning of a single individual can outweigh the authority of 1,000 men. And so we tend to deify these people. And it's just natural because humans love to have idols to worship. But ultimately, I think that undoes a little bit of the scientific method each time it's invoked.
Separate the person from the idea and look only at the idea. Now, we have a sort of situation going in particle physics, W boson, I believe, where we now have a much heavier measurement of it than previous measurements, suggesting a discrepancy. What are your views here? Do you think that maybe we might be putting too much emphasis on a single experiment just because it's from a very credible source?
It's a very good question. So we have an example now of not new experiments, not the new construction or new data from, say, the Large Hadron Collider or even Fermilab. We have a reanalysis of these very unusual particles called W bosons. So normally the most familiar boson to all of us is boson the clown. No, I'm just kidding. Is the photon. The photon is a boson. It obeys Bose-Einstein statistics. It participates in the Planck distribution, the blackbody radiation law. It is a particle that can have an infinite number of accompanied particles in the same exact quantum state, in contradistinction to a fermion, which has only one quantum entity per quantum state. So these bosons, though, are charged, unlike the photon, unlike the Z particle, unlike the Higgs boson. The W is kind of this freakish particle that has sort of properties like a fermion, like an electron and a positron, where they can have particle-antiparticle pairs that aren't themselves. So a photon's antiparticle is itself, and these W particles have antimatter conjugates to themselves, but they're also charged. So they're very odd particles. And as such, we can look for departures from their expected behavior with great precision because unlike, say, dark matter or even photons, they are charged. So you can hope to play around with them a little bit more than just, say, by their gravitational or their nuclear properties. So what was found by Fermilab data analysts, it wasn't new data, it was old data reanalyzed, was not that the boson itself was 5 times heavier than we thought, but the precision at which we knew its mass departed from the prediction by theorists that we call the Standard Model, departed from it by a very large amount in terms of statistical significance. So for that reason, it's considered to be a challenge to the Standard Model. Now, won't really believe it's a crisis until it's replicated, perhaps with new data. It's not to say I'm questioning the experimentalists, the data. This was done at Fermilab, I think 15 or more years ago, at the so-called CMS, or compact muon solenoid experiment there. So there is still yet some probability that this could be not replicated. And so I want to reserve judgment before we start really freaking out about it, although it's always fun to speculate what it would mean. And I think a lot of what it could mean, if it does hold up, could have bearing on forces and obviously fields beyond the Standard Model, meaning that there could be other force mediators. All bosons are mediators of a type of force. The photon mediates electromagnetism, and the W and Z bosons, they mediate the weak force, and together they mediate the electroweak force. So it could mean that we have to add an even another particle, maybe a Q particle or some other letter. So we just don't know is the final answer. But I think the question will be resolved in the next few years by more and higher energy experiments, like some being done at the Large Hadron Collider.
Which it's worth reiterating that this could mean, if it pans out, this could mean a fifth force of nature, right?
That's right. So we've heard a lot about fifth forces, and we do believe that there's reason to expect a potentially a unification of forces, meaning that there could be, as you go up higher and higher in energy, you can start to see that the forces lose their individuality and become manifestations of a combined or composite force. So, for example, it was once thought that magnetism and electricity were two separate phenomena. Maxwell unified them. And it turns out they're unified at the temperatures that they're not manifest. The difference between them is not manifest at temperatures, say, like at room temperature, what have you. In the proper way of looking at it, you can actually transform an electric field to a magnetic field in the proper context of treating them using relativity and Maxwell's equation, so that at room temperature you can have a current carrying wire that produces a magnetic field where you have charges in motion, which is an electrodynamic process, produce a magnetic field, for example. But then you can ask, well, how are those charges moving? If I accelerate to their velocity, they would seem stationary to me and they'd only have an electric charge. So that's an example of the unification of electricity and magnetism, depending on reference frame. What we do believe is that if there are other forces, their unification would have to be sort of visible as a function of energy and then bifurcate and then not be part of a unified force. So the electroweak force is the combination of the weak nuclear force with the electromagnetic force, meaning that the W and Z bosons and the electrons and positrons of electrostatics can interact with photons. And so that does happen. Now the question is, do you have to add in another boson to then produce an interaction between the forces that are already mentioned? So there could be another boson, like I say, that then modulates the force produced by the W and Z bosons. And that would be really exciting. But again, we don't really know. And it's a little bit early to really get too deep into the speculation of a fifth force. But there's nothing that prevents that from being true.
The unification of forces, do you think it's possible that this could just simply be messy? A messy aspect of the universe, an inelegant aspect of the universe, and that they never unify?
Well, it's often said that we're waiting for the unification of the strong nuclear force with the electroweak nuclear force. And that would be called a grand unified theory. And I think for many people, they're actually skipping that step. They're actually thinking of what's called a theory of everything, where you unify the strong force, the weak force, the electromagnetic force with gravity. And of course, the best studied and most popular scenario for that is called string theory. We have no evidence for string theory, yet that doesn't stop people from working on it. And yet that would occur at extremely high energies trillions of times larger than what we can probe with the Large Hadron Collider, for example. But even with the Large Hadron Collider, we might be able to get glimpses of a grand unified theory, but maybe not, because that might occur at energy scales 10 or 100 times greater than the Large Hadron Collider can produce. So I always joke that we're putting the toe before the gut. In other words, people like Stephen Wolfram or Eric Weinstein or Sheldon Glashow or Edward Witten, they're looking for these theories of everything, but we don't really have a good explanation for grand unification. We don't even know if grand unification takes place, let alone something at 10 or 100 times higher energy, or 1,000,000 times higher energy, like a theory of everything.
And this is why we keep building bigger particle accelerators. Now, in experimentation and trying to prove something like string theory, it's great to formulate it and it's great to talk about it, but so far I haven't seen a way to experiment with it. Do you think that there is anything in the future for string theory to be able to at least try to start getting some indications that it might be the case? And I'm going to attach something to this question. The idea of other dimensions of space and time. I believe that in most variants of string theory, it's 10 dimensions of space, 1 dimension of time. And do you think that that might be the key? I mean, is there a way that we could look and see if other dimensions exist? Because maybe we have an indication of that with spooky action at a distance.
Yeah, so there's a lot there. The question of whether or not we can collect evidence for string theory, I think, has to be separated from, say, looking for evidence of a fifth force or from departures from the standard model. So, for example, we can look at string theory and we can say, well, what would you predict for the magnetic moment of the muon, say? And why would that prediction be different than the standard quantum field theory approach? And then you could compare that to what scientists measured using this G-2 experiment, which is also an older experiment, 20 years old experiment, but getting a lot of attention lately. And then what you'd like is that they make a prediction, like Galileo made a prediction. If you cut the rope in half in midair, both sides fall at the same speed, even if they're at different lengths or weights. So you'd like that prediction, and that's actually using I should have called it a string, testing string theory with Galileo. But the prediction should come before the observation if you already have a good deal of credulity in the underlying theory. The problem is that what string theory does really well is it provides a way to quantize gravity and incorporate gravity, and that's where it came about as a first attempt, that gravity naturally emerges from the replacement of zero-dimensional point particles with tiny oscillating, vibrating one-dimensional objects called strings. And there are many modifications to it, like superstring theory, which adds on this symmetry between bosons and fermions that, again, this has also not been manifest in any way experimentally. So the problem is we don't really have a lot of data for any of these things. Some of these things, again, took decades to measure the first time, and then typically what a scientist wants to do is get on to the next thing after they verify some prediction or maybe make a serendipitous discovery. We see that throughout the history of experimental science. So sometimes the experiment is far in advance of the theory, but other times, like with string theory and supersymmetry, the theory is just way out of pace with what could ever be probed with an experiment. Talking trillions of times, trillions of trillions of trillions of times higher energies than can be probed with modern day accelerators. And by virtue of the very expensive scaling of the size and energy of a particle accelerator with its diameter, it's almost inconceivable that we'll ever build anything much bigger than the Large Hadron Collider.
Now, that's the problem. Yeah. That's the fundamental problem, is that there could be theories that we'll still have 500 years from now because there's just simply no way to test them realistically.
Yeah, so you may. Well, I shouldn't say that we can't test them. It's just that we can't use the standard pattern of testing things that takes us all the way back to a trillionth of a second. It's very interesting. The Large Hadron Collider can make 10 TeV, center of mass collisions. And it can do that trillions of times a second and collect tons and tons of data. If you ask, how old was the universe when every photon in it, more or less, had a characteristic energy of 10 trillion electron volts? Turns out the universe is about 0.2 of a trillionth of a second old. So that's quite fascinating. We can actually replicate the universe after only a trillionth of a second after the Big Bang. The problem is to go back farther in energy. It goes as at least the square of the energy to go back in time. It goes as the square of the energy. So if you want to go back to 1/10 of a trillionth of a second, you need to come up with 4 times more powerful Large Hadron Collider. And it's hopeless to think about going back to, say, the Planck time or even the time at which inflation occurred. Now, there are processes occurring in the universe producing massively energetic particles that we can detect, and that we are effectively using a supernova or a black hole accretion disk as a particle accelerator, far more powerful than anything we could ever construct on Earth. And those instruments are producing kind of interesting results that seem to indicate anomalies that would need to be explained in some way. So we do need to understand those, and those could have implications not only for high energy particle physics, but for the laws of fundamental symmetries, such as parity, charge, time, inversion symmetries, so-called discrete symmetries that we know and love. And then that could even have further implication, as it's been described in the press, for so-called anti-universes, multiverses, and so forth. So it's not hopeless. There are ways to probe it, but it's a very tough game to play.
The anti-universe. Now, you recently did a video on this, and so did I, and exploring this idea of a universe, a twin that stretches backwards in time. Do you think that this actually has legs, this idea that there could be a twin universe? Now, and this invariably is going to get into weird stuff like multiverses and the many worlds interpretation and things like that. But just on its face, just the idea of a universe stretching backwards in time from the Big Bang as a twin of this one. Do you think that has legs, or do you think it's just too speculative?
I think it's too speculative, but it's not uninteresting. And it's what I like about this idea. I don't like the hype surrounding it, and I did a video about it. I've done interviews about it with one of the leaders of it, Abby Viereg, who's a professor at the University of Chicago. She played a role in the experiment called the UNITA experiment, which is an Antarctic balloon experiment, lofting a radio telescope above it, not looking up at the universe and the sky, but looking down at the ice using the vast treasure trove of highly purified ice in Antarctica, where I've been 2 times, lucky enough to have been there 2 times to do the BICEP experiments. That ice provides a laboratory of massive volume of highly purified reagents and reactants to then use as a detector for exotic particles, including the so-called poltergeist particle called neutrinos. When we look at neutrinos, they were some of the last particles to detect in the fundamental elementary particle zoo, of which there's only 17 particles. They are the only ones that don't have a known mass of all 17 elementary particles. Since 2012, when the Higgs was measured, we now know the masses of 14 of the 17, and the ones that we don't know are the 3 flavors of neutrinos. Now, some have speculated there could be a 4th flavor of neutrinos, if you will, or another type of neutrino that is its own antiparticle. Neutrinos are fermions. They typically have antiparticles with opposite charge. If they have charge, these neutrinos obviously don't. So Anita saw these radio signals from the rough analog of Cherenkov radiation. When you have a particle moving faster than the speed of light in the medium that it's traveling within, it produces a ghostly type of light called Cherenkov radiation. You may have seen if you look at nuclear reactors, where you have light traveling, or you have particles, energetic particles, traveling in water, and those particles can travel faster than the speed of light in water. So the speed of light gets reduced by the so-called refractive index of a material, which is dependent on its dielectric properties. So these particles can travel faster than that. So too can neutrinos travel faster than the speed of light in the ice of Antarctica. And when they do, they don't give off bluish Cherenkov visible light. They give off radio waves. And what Anita detected, this is almost 10 years ago now, but for some reason it keeps getting pushed to the front of the public's frontal lobes. And that is, there have been 3 anomalous events, 2 of which are explainable, maybe one is not. And they projected a hypothesis that these neutrinos were traveling in ways that were inconsistent with the standard model. So there have to be either one type of explanation that's more prosaic than another. It could be an astrophysical source, like a supernova explosion that produced these that happen to not interact going through the entirety of the Earth. and somehow emerge unscathed to be detected inside of the Anita telescope. There could be this flaw or random fluke fluctuation. They don't rule this out. The Anita collaboration doesn't rule this out. Or it could be something strange that we don't expect to exist, or we've never seen to expect to exist, that the universe doesn't obey these fundamental symmetries that you and I talked about, I believe, early this year or late last year, which is called CPT violation, or a further kind of description as Lorentz invariant. So there are certain laws of nature, including most laws of physics that we're familiar with, that are invariant under simple transformations. So if you change the charges from negative to positive of all the charges in the universe, the physics doesn't really behave differently as long as you change the direction of time. There's another symmetry called parity symmetry, which is that if you look at, say, a pendulum swinging in a mirror, you can't tell the difference under reflection that you're looking at the object directly or you're looking at its mirror image. That's called parity symmetry. And then there's time translation symmetry, which is that if you change the arrow of time from positive to negative, the laws of physics are invariant as well. So if you look at, say, the Earth rotating around the sun, if you look at it, you would see the Earth, and now all of a sudden you reverse the direction of time, the Earth would go backwards, but then you also have to reverse the direction of velocity, so the Earth gets a double negative, and so it goes in the same direction. So the laws of physics are invariant under these three symmetries. Now, if these neutrinos are, so in our universe, if you like, this universe respects CPT violation. But interestingly, it doesn't respect CP violation. I'm not sure if anyone's ever tested CT by itself or PT by itself, but in all physical circumstances, the violation of CPT is not observed. Thus, if these neutrinos were behaving as if they were both their own antiparticles, and they're also viewed in the antiparticle sense as coming within our universe, then it was thought that is inconsistent with CPT violation being preserved. So it's a long way of saying that you need another universe where CPT violation takes place. And those particles would travel somehow into our universe, and this parallel universe would be giving us clues about its existence. Now, that's pretty far-fetched. So I don't like that idea as itself, but notice the chain of reasoning. It came from ideas about symmetry. It was detected by a balloon-borne telescope on a very pure substrate, the Antarctic ice, and using known laws of physics, analogous to Cherenkov radiation, looking at new known particles, neutrinos. So all the individual rungs on this ladder are worth putting your weight on, but together they don't exactly point you in a first guess towards an anti-universe. So that's where I diverge. But I think the whole thing is built upon solid science, good experimental practices, but the jump to the public's imagination is a little bit far-fetched. And the last thing I'll say is that we tend to get a lot of hype around these things. And I always say, the hype or the detection, that always appears on page 1. In this case, it was in the New York Post, not a journal known for its scientific acumen, but we'll leave that for another podcast, perhaps. But then when scientists refuted this or claimed to have refuted it in using the ice cube experiment, there was no retraction published on the front page of the New York Post. And I find this a huge problem with science because it leaves the public with a misapprehension, both of how science is done and how the results are changeable and reflective of the scientific method by virtue of the fact that they change. If they change, scientific consensus has to change along with it, as I said in the context of Galileo at the beginning of our conversation.
Now, we have a hard out today because Brian has a night career as a superhero, crime-fighting superhero, and I have a meeting of my monthly cheese tasting club. Mm-hmm. So before we go, Brian, where can everybody find the audiobook?
The audiobook is on my website. It's on Audible or it's on Apple Books, but the easiest way to find it is on my website where I have a discount. And my website is briankeating.com/dialogue. And I urge you to join my mailing list because I give away things like meteorites, and I even give away copies of this audiobook. I have a giveaway that's going on now to 5 people, so you can sign up for the giveaway. But I also, John, I just started something interesting that I think Galileo would have been interested in. I just minted my first NFT. And the NFT project that I'm hoping to gain some support for, and it's sold. I sold it for a decent amount of Ethereum, actually. And what I sold was a portrait of Galileo from the actual book, the dialogue. And it gave me a wonderful idea. And maybe with the help of your audience, we can make this happen. My goal is to raise enough money to buy a first edition copy of the dialogue, which is first printed in 1632. There's only a couple hundred of these that exist, and they're usually locked up by people like Bill Gates in underground cellars that he uses to wipe his face. I don't know what he does with it. I'm just joking. Hopefully he doesn't use it to put his pizza on, but I doubt he does. But anyway, there are not so many of these. So what I want to create is a so-called distributed, or maybe it's digital autonomous organization, or DAO, in which folks like me and people in your audience combine to govern and to take care and steward these great works of literature that are also great science books as well. The dialogue is a phenomenal read and listen. We portray it in dialogue format with two Italians and a New Yorker, yours truly. So I'm hoping to get the funding to do this from a community crowdfunding using Ethereum, using NFTs. And these books cost over $100,000, so it's more than I have as a public employee of the state of California. But nevertheless, if we can get enough interest, what I will do is hopefully get the ability to buy one of the copies of the dialogue from 1632. So it's 390 years old this year. And in 10 years from now, hopefully we'll have enough money or less to buy a copy of it. And then we'll have opportunities for people in the DAO to interact with the book, to turn its pages, to read it, and then eventually we'll steward it somewhere, perhaps at the University of California Library, where it can be held under armed security, but still accessible to young people like your audience. So anyway, it's kind of a side hustle because I needed some more to keep me busy.
All right, there will be links to all of that stuff in the description below. And thanks for joining us yet again, Brian, and we'll do this again soon.
It's truly my greatest pleasure, guys.
Once again, thanks to Fishing Clash for sponsoring this video. Don't forget to download the game through the link in my description or by scanning the QR code. Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.